just start the recording so I don't forget it. Okay. Well, today's topic is very exciting. The first detections of tidal interactions in exoplanets. I was very surprised to see that we could measure it in light curves.
It's been a long time that we want to do that. I'm clicking the wrong button.
Is WASP still up and running?
Actually, I don't know. I thought that not as a survey. I'm not sure, but they were using the telescopes to do some follow-up of some planets. But to be honest, I don't know. Some years ago, they were still running, especially maybe the ones from the south. But now I don't know.
Most of these Earth-based missions were in Chile, I suppose, based.
WASP no. WASP was in the
No?
Canaries. There was one station in the Canaries, and the other one is in South Africa.
Okay, that's nice.
There was, I think, the HAT. They had one maybe in Chile, and then also one in South Africa, and maybe one in Australia.
Okay.
And there's a few now in Chile, the new generation, next generation WASP and GTS.
Yeah. Wow.
And Mascara.
Okay. Sorry. Well, we are already 2 minutes past our time. People will still join us, but let's go on and start. So let me just make a short introduction. Okay, so hello everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linear MCTI. Today we have the honor of having Dr. Susana Barros from the Instituto de Astrofísica e Ciências do Espaço. Dr. Barros is an expert in exoplanets, with her research mainly focused on the detection and characterization of these extrasolar worlds. Having been involved in the discovery and characterizations of dozens of planets, Dr. Barros contributed to several Earth and space-based projects such as WASP, Corot, Kepler, and K2. Currently, she's involved in the ESA exoplanetary transit-based missions CALPS, Plato, and Ariel, as well as in the development of high-resolution spectrographs to measure planetary masses. She also contributed to developing the pipelines to the Corot satellite and to reduce systematic noise in the K2 satellite light curves, among other transit modeling tools using Bayesian statistics. Dr. Barros, thank you very much for being so kind and having accepted to give us a webinar talk today on such an exciting topic. The floor is yours.
Thank you. Thank you very much for the introduction and for the invitation to give this talk, to tell you about my new results on the observing the tidal deformation and trying to measure the tidal decay of WASP-103. So I will start with an introduction to exoplanets. Then I'm going to tell you about more information on tidal decay and deformation and what we can get if we can measure them. Show you our observation and results on WASP-103, and finish with our future plans for measuring tidal decay and deformation. So first, I'm going to start with the basics of a transit. So in the cases where the planet is aligned with our line of sight, we can see a transit of the planet in front of the star that leads you directly to the size of the planet. Much more information can be assessed for planets that transit their star. For example, when the planet goes behind the star, if the planet is hot, we can also see a dip in the light curve that gives you access to the temperature of the planet and information on its atmosphere. And also when the planet goes in front of the star, there's some information on the atmosphere. These planets are so valuable that there's been a huge amount of surveys that were dedicated to finding them. So although they are rare, now most of the planets we know are transiting, but just because we have focused on discovering them as such. So first there was these surveys from the ground that were detecting hot Jupiters, very big planets close to their stars. Now the next generation ground-based surveys are focusing on smaller planets. And to go towards longer periods and also smaller planets, there's been some satellites that were launched, like first one was Coho and then Kepler that found a huge amount of planets. And now TESS is finding a lot of bright planets around bright stars for which we can get radio velocity observations to also measure their masses, and CHEOPS is also trying to help with the characterization of these planets. In the future, Plato will be our best hope of finding an Earth-like planet around a Sun-like star. So a planet the size of the Earth in an orbit around 1 year orbit around its star with a temperature that could host life, as we know it. Can you see my cursor?
Yes. Yes.
Okay, thank you. Okay, so all these surveys have discovered a huge number of planets that show a very large diversity. So you have here planets that are like Jupiter, but much bigger, but they are inflated to form planets that are like the Earth. And surprisingly, most of the planets that were found have sizes between the Earth and Neptune. You cannot see it very well here, and we don't really understand very well its composition. If they are giant planets, or that are small giant planets, or big rocky planets. So if they have a big core with a small atmosphere around them, or if they have a huge atmosphere around a small core, or they are just ice and mostly gaseous bodies. So this, you can see them here. This is a better updated plot that is zoomed in the part close to the Earth's size. And you can see here the large number of planets that have been characterized with these characteristics, slightly larger than the Earth, and also with a mass slightly larger, and the compositions that they can have. But this is a bit degenerate, so it's difficult to really place them and try to understand their internal structure. And for that, there's been a lot of observations. There's been the launch of some tests and Plato to try to find more of these planets, and also to push towards the Earth. This is the next frontier, characterizing planets closer to the Earth and with the incident fluxes, so with temperatures or effective temperature that are close to the Earth. Because most of these planets are much hotter, as you see here. They are color-coded and they are much hotter than the Earth. Another way of seeing this is this plot that shows you the planet mass versus the major axis. So this is the Earth, and around the Earth there is not lots of planets. There's nothing. This here, there's no cuts. In here, I think I forgot to say, but there I just show the planets that have precision in mass and radius better than 30%, because if you have less than these, you really cannot tell, because the errors, they encompass all of the compositions possible. So you have to have much better than that, and normally 10% in mass and 3% in radius to be able to decide which composition the planets have. And in this case, I didn't do any cut, and it's only the masses here. So maybe this planet's not even transiting. So here there is really not any planets known, and we are trying to push towards measuring masses of planets at orbits like the Earth. So the work that I am going to speak to you about today was made with Cheops. Cheops is a satellite that is pretty small, like Koho is smaller than Kepler. It has a 30 centimeter aperture, and it's focused on only one star. The field of view is rotating around this star that is our target. We can almost observe any part of the sky, not 100%, but it's close to 100% of the sky, point to any star, but not during the whole year. Depending on the season, we can point to different parts of the sky. And because we're just focusing on the target, we can just choose the target that is interesting, but we cannot see anything else except for these targets. Okay, I think that's mostly it's in a polar orbit around the Earth, as you can see here, is orbiting the terminus of the Earth. Okay, so these planets that I'm going to focus on, because they are the ones that have measurable tidal decay and deformation, are the hot Jupiters. These are the first planet that was discovered was a hot Jupiter. This was very surprising because in the solar system, the planets that are big like Jupiter are thought to have been formed, and they are now beyond the ice line. And this is because of this part of the accretion of the disk was much easier to accrete more matter and form. First there was ice, and they would form big planets with ice and gas. So it was very surprising to find this planet so close to the star. It is possible. There are some theories that can create a planet in situ, Jupiter, but they are very difficult and they are very fine-tuned to form a Jupiter so close to the star. So the best explanation we have now is that these planets have formed further out in the disk, and then they migrated inwards. And they could have migrated through this migration. So this is like a slow process, the interaction with the disk. The planet slowly migrates inwards, or they could have been a more violent migration with interaction with another planet or star that made their eccentricity increase a lot and also tilted the orbit. And then the planet slowly, by tidal migration, reached this configuration of where you see it now. In this case, we expect to see a difference between the axis of the star rotation and the orbit of the planet. And this has been seen for many planets. So we think this is at least lots of planets have been formed through this, if not all, through this mechanism of high centricity migration. Okay. To connect to the rest of the talk, the way the planet migrates depends on the tidal interaction with the star. So it's important to constrain the tidal interaction to better understand also this evolution of planetary systems. And here I show you the equipotentials of a two-body system. And the planet and the star are not up to scale, but one thing that I try to put to scale is that the planet, that is the hot Jupiter, is almost filling its Roche-Lobe. So in this two-planet system, close to the star or the planet, the gravity is dominated by the body that is close to. But then when you go further away, the influence of the other body starts to be felt, and then the sphere of influence of the planet in terms of gravity decreases. So here in this Roche-Lobe, it marks the sphere of influence of gravity of the planet over the star. Due to the planet's surface has to follow these equipotential lines due to the equilibrium of hydrostatic equilibrium, and the star too. So in these systems, the star is also not so close as the planet, but is also deformed, and ellipsoidal variations have been found also in the light curve of the star. This has been seen also for planets, but mostly for binaries. But for planets, this has never been measured. The variation on the light curve is too small, and now we try to do this with the transit light curve. The tidal forces on these systems, they tend to circularize the orbits and to synchronize the rotation of the planet and the star with the orbits. In these systems, the fastest phenomenon are the circularization and also the synchronization of the planetary rotation with the orbits, and the star rotation is still not synchronized with the orbits, and there's not enough energy to do it actually. So the star period is normally around 20 days, maybe 10 days to 30 days, while the planet's orbit in these systems, the ultra-hot Jupiters, is 1 day or less. And hence the star is rotating slightly slower than the orbits, and there is there's a lag between the bulge of the star and the line of centers that leads to a tidal torque on the star that tries to increase the rotation of the star and removes angular momentum from the planet orbit. So the planet starts going inwards, losing angular momentum, and its period shrinks until eventually it falls into the star. There's not enough energy to give to the star to stop this. So in principle, the planet will eventually fall in the star, and we are seeing the last stages of this planet evolution. We are trying to measure this tidal decay and deformation using the CHAOPS. There's a group called fixture characterization within the CHAOPS GTO, guaranteed time of observations, that I am leading. And in this group, besides the tidal deformation and tidal decay, we also are searching for moons and rings of long period planets, and we are trying to measure the spin orbits alignment using gravity darkening. And this only happens for fast rotating stars. So these three objectives in this group. There's other groups in CHAOPS that are focusing on atmospheres, on measuring best radius for planets. There's other groups that are doing other science, as you might know. So in this part of the group, in this program that is tidal deformation and decay, we have some targets, 2 targets for tidal deformation and 7 for tidal decay, to try to do these measurements. So as I told you, the tidal decay will lead to a shrinkage of the orbit of the planet. And if we can measure this shrinkage of the orbit, we can measure a parameter called the tidal quality factor, that is also named Q, that is depending on the star structure, and is very important to constrain stellar models. As I told you before, it's also important to try to understand how hot Jupiters evolved and what happens, how they stop migrating, or how they end up where they are now. This value, the tidal quality factor or tidal dissipation factor, has been estimated from theory to be in between 10 to the 6 and 10 to the 8, from observations of binaries from 10 to the 6 to 10 to the 7, and from some statistical measurements of hot Jupiters to be a bit higher, 10 to the 8 or 10 to the 7. So, and they think that there's 2 types a binomial distribution of Q. So there's stars that will have a Q that is 10 to the 8 and some that would have 10 to the 7. And this could be due to the temperature of the star, since stars that are hotter, they have they might have a faster decay due to their atmosphere dynamics. Here in this plot, I show you an estimation of the tidal decay for the known systems. The equation is here on the top of the expected period derivative, and assuming Q is 10 to the 6, we made this plot that shows planet mass versus, that is this part of the equation, versus stellar mass, and orbital distance versus stellar radius. So then in this plot, if you can draw lines of constant decay, and you can see that the systems that are expected to have a larger decay are these WASP-12, WASP-103, CAT-16, WASP-18. So are all targets for KEOPS. Some of these cannot be observed with KEOPS, but the ones that are expected to be higher, we try to observe them with KEOPS to try to measure Q. The only planet that for now has a measured orbital decay is WASP-12. And you can see here the observations that had led to this conclusion. First, maybe you can check the equation for the variation of the time. So this is, if you assumed orbital decay, you can approximate the orbital decay by this equation that is a quadratic equation. After you remove the linear parts from this equation, you get these times. They are deviation from the linear ephemeris, and they have this shape for tidal decay, a quadratic model. Besides orbital decay, also upside precession could have the same shape, but orbital decay will continue forever until the planet falls in the star. But upside precession is actually a sinusoid, so you can see here in the equation. It's a sinusoid that will change. The planet first appears to be decreasing period, and then it will increase period in a cycle, sinusoidal, among a mean period. So you can, if you continue observing it, you can distinguish, and you can also try to distinguish this using occultations, because if the planet is decaying, both the transits and the occultations will appear earlier as the period decreases. But if you have upside precession, this the transits and the occultations will behave in the anti-correlated. If the transits appear early, then the occultations will appear later, and I will show you why. So here you see a system that it has precession. So if you're looking at the planet from here, you will start observing transits that are earlier as the planet precesses around the star. But the occultations will come later. This is a bit difficult to see, but maybe you can believe that it will appear, the transits will appear earlier, and the occultations will appear later. And this is very different from if the planet is just spiraling into the star. Okay, the second planet for which there is a measurement of period decrease is WASP-4, but in this case, we don't know if this is due to orbital decay or upsidal precession, because there is not a lot of occultation measurements. Sorry, I forgot to tell you, but the Q in this case is measured to be 10 to the 5. And this is much lower than what I told you before, of 10 to the 6 to 10 to the 8. So it's one of the reasons why people in the beginning were not very convinced that this was actually tidal decay. And in this case, the Q measured is even lower, higher. Lower, sorry. and is much lower than it's expected. So the dissipation is higher. So it's stronger dissipation. The variation is higher. The stronger the dissipation here is, the lower the Q is. Okay. Yes, so other effects besides the upside precession can affect the transit times, as I will show you later. But for the tidal deformation, if you imagine the decay potential and the rush flow there I showed you before, if the planet is following this shape, as it transits in front of the star, it has a slightly different area of occultation of the star as it rotates and orbits the star. And maybe it's easier to see it if there is an inclined orbit. You see slight difference in the area that the planet occults, and this leads to a variation of the size of the planet as it transits, and a variation of the transit light curve. And the difference between the mean radius of the planet and the deformed planet is shown here. And this was a model made by Correa that showed that you can relate the variation of all the axes to a single parameter, that is the love number. So you just include one extra parameter in the fit of your transit light curve. And this, besides just being one extra parameter to be able to derive the deformation, it's a very interesting value that measures the distribution of mass within the planet. And if you get you can lift degeneracy in internal structural models. It helps you to calculate the size of the core, the amount of how matter is distributed inside the planet. With a PhD student, and before CHEOPS was launched, we prepared the observation we tried to see if it was possible first. So we we used the model of Correa, the equations, and implemented them in a transit code to be able to then we simulate transits to see which of the planets that are known would give the highest signature, and we found it was WASP-103 that you can see here. We also found that this signature was slightly different than the one that was suggested by Correa, because we don't actually know the mean radius of the planet. And what we had was a light curve, and what we have to do is fit the light curve with the spherical model and with an ellipsoidal model. And the difference is the signature of the deformation, and that is what is seen here. It's slightly different. It's actually a bit smaller than what was the theory of Ocean Correa. And the shape is not very deep, but there's some differences. Our first estimates said that we required 300 CHEOPS transits or 100 Plato transits to be able to measure this. For the best case, that was WASP-103. But as you've seen, we were a bit pessimistic, and we managed to do it with much less data. Before our observation, the only measurement of the love number, or a hint of the detection, was made as 2 sigma using 2 HST transits of WASP-121, and you can see here. And this was done by Hallard. The love number is very interesting, and there's only another way that you can measure the love number of exoplanets, and this was made for HAT-P13 that is in a very specific dynamic configuration. There is the planet, the hot Jupiter, has a companion, and both planets are interacting, and their eccentricity, the outer planet made a small eccentricity on the hot Jupiter, on the short period hot Jupiter, and that makes the orbit process and the precession of the orbit depends on the Love number. So if we measure the precession of the orbit, we can measure the Love number and the eccentricity. And this was done first. We just get the first measurements led to a slightly large constraint on the Love number, or a large error on the constraint that led still already to a measurement of the core or a constraint on the core. But the latest results give a very precise value for the Love number, and a very precise, the best value ever for an exoplanet to estimate its core mass. And maybe if you have known, but for Jupiter, it was also difficult to decide if he had or not a core. And this was finally, lately has been measured and with the space missions that measure the quadrupole moment that is similar to this Love number. It's a similar measurement that give you access to this constraint on the interior structure of planets. So this was the first detection of a deformation of a planet, of this departure from sphericity, and hence it was an important result that led to his press release. You can see here the press release that I'm going to use to explain a bit more the system. So WASP-103 is slightly hotter than the Sun. The planet orbits at less than 1 day orbit, and has 10% of the size of the star. It orbits very close to the star at 3 stellar radius is the distance of the planet. So it's really on top of the star. The radius is one of the larger, it's been found to be larger than what we thought, and it's with one of the largest hot Jupiters known. So the planet is inflated and slightly more massive than Jupiter. It's also very hot since it's so close to the star. It's very hot planet, and from its internal structure, we think that is very similar in its internal structure to Jupiter, despite this being so much hotter. But a much better constraint on the Love number is needed to be able to tell more about the internal structure of the planet. So to do this, we have collected 12 transit light curves from Cheops that you can see here. There is a lot of noise in these light curves, and this is instrumental noise due to this fact that the Cheops is rotating continuously around the targets, and any star contamination, any pixel, any variation gives rise to this variation of the light curve that it can be seen, and that is in the period of the orbit of Cheops. And this can be corrected very well, completely, using several methods, but in this case, you use a multi-dimensional Gaussian process that is using the instrumental parameters, the most important, the roll angle, but also the position of the star and other contamination parameters. And you can see here, and this is modeled simultaneously with the transit, and you can see here from the residuals of the fit that we really reach almost photon noise. So our model of the systematics and the transit is working pretty well. From Cheops alone, we could not measure this Love number or the deformation, so we had to include combine our data with other data that was taken before, and we use Spitzer data as an infrared telescope in space. We had 2 bands with Spitzer and 2 HST Hubble Space Telescope data of the planet that is phase folded here, besides the 12 phase folded light curves of Cheops. And here in this plot, I show you the points, the observations done in black. Then on top, you have a model that is the ellipsoidal model of the planet. And below, there is the residuals of this ellipsoidal model in blue, and the residuals of a spherical model. The difference between the spherical and the blue model is not visible if I try to plot them on top of the data. And so you just you have to concentrate on this part bottom down. You will not see it. There's no point in plotting it. And the signature, as I said before, the signature is that we are trying to measure is here in the difference between what we observe and a spherical model. And is shown, the best fit model is shown in green, and as a zoom of this is shown in below. And this is changes with wavelength. I will show you a bit later. So we cannot put all of these results together. Different combination of these light curves give different significance of detection for the planet. And if you combine everything, we get the 3 sigma detection of the log number, and hence the deformation of the planet that we were hoping for. And here I show you how the signature changes with wavelength. And it changes because of limb darkening, because limb darkening also changes with wavelength. And it also changes because the size of the planet is bigger in the infrared because of the atmosphere. So we are also detecting the atmosphere of the planet. And here I show you also another important point of our modeling is that if you don't account for deformation, we get a large error in the radius of the planet. So here I show you the results of the spherical model and the ellipsoidal model. These are corner plots, so the distribution of the parameters are on the top and the correlations below. And you see that if we don't account for the deformation of the planet, you have a much smaller error on the parameters because you have extra the extra parameter that we put, but you will have a really big difference between the measured radius, and that would lead to an error in the radius and the density of the planet derived. And even before we have made our discovery, we were expecting the planet to be deformed, so people would make assumptions on how much deformed the planet was to try to correct the radius of the planet. And even so, we found it to be larger than what was thought before. So also important in this figure is the detection. Here, this is the log number, and you can see that we got a 3 sigma detection of the log number here. And the reasons why we managed to get a 3 sigma detection with just 12 transits of chaos, although we included other transits of very high precision data like the Hubble Space Telescope. We found a larger radius for the planet, so actually the signature is larger than what we expected. We improved our model, and we also get strong limb darkening constraints. And here I show you, but I will not spend a lot of time. This is a bit complex. If you have questions, please let me know in the end. So here I show you how we got a better constraint of the limb darkening. In the beginning, we are using very large errors for the limb darkening. We derived limb darkening from theoretical models, but then we included a large error. So we fit it together with the transit with a large error. And the theoretical models are this. We were using Phoenix, that is this line here. And then what we did was that we also checked another model that was Atlas, and see how this compare, and we fitted the limb darkening with the 3 different laws, and then we increased the errors of the fit so that they encompass both models. So increase the errors by between 5 times and 40 times for the quadratic model that is thought to be the worst to reproduce, but you also can see here that is actually the worst one that reproduces even this plot. We needed to increase the errors by 40 times the intrinsic model errors. And we also, so we did this with 3 laws. For the 3 laws, we got limb darkening love numbers that are in agreement, as you can see here, and we also got significance for both the power 2 law and the nonlinear that are thought to be the best descriptions, especially the nonlinear is the best description of the limb darkening that we know, while the quadratic has been shown in the literature to have given poor results. Besides the tidal deformation, we also try to measure the tidal decay of WASP-103. Here I show you in black the previous values from the literature that I had gotten from this paper. Here we derived that it was not available, the values for the Spitzer and the HST data that is seen in kind of pinkish, and then the new transits of Cheops in blue. The previous solution is in green, and you see our new solution in red. And you might be surprised that in this case, the parabola is going this way instead of the expected tidal decay signature that is supposed to be like this, because the period is supposed to be decreasing. And indeed, this is not expected. We found a period that is increasing, so not in agreement with tidal decay. But within 3 sigma, this is an agreement with tidal decay, and we can put a limit on Q to be higher than 10 to the 6. So this is higher for sure than WASP-4 and WASP-12 that have been measured. This could be, this variation that is seen here is not significant. The best model for the transit times is a linear model. So it's not supported by Bayesian statistics. But if in the future we find that actually the planet is increasing its period, it could be through these 3, at least these 3 effects could have be the cause of this. The first one is RV acceleration due to a companion. It means that if you have a star in the or a very massive planet that is orbiting the WASP-103, this can pull WASP-103 to be in its orbit around the center of mass, to going away from us. And if WASP-103 is moving away from us, you would get transit timing variations due to the arrival of the transit time, the light travel time effects that will give you this difference of transit times. We actually found a companion that was known, a companion to WASP-103, and we calculated if this could be the cause of this variation of the transit times, and we found that it could be within the errors, because our errors are as you can see, they are compatible even with the non-variation. So it can be. We made further observations of this star using lucky imaging, and we don't find it. And this is either because we cannot get enough resolution, or that the star went behind WASP-103. And if it is so, then the star will not be bound. It could not be bound. It was moving too fast to be bound. But it's still under discussion. The other 2 effects that could have created these variations in the period is the Applegate effect, that is variations of stellar activity lead to variation of the quadrupole moment of the star that is being seen in binaries, and estimations, very rough estimations, give that this effect could be 38 seconds. It's very, very poorly understood. And we don't even know that if it's going to affect planet's periods. But it could also create some variations of the times, and also upside of precession, as you saw from Mahat 13. So if the planet, for some reason, has an eccentricity, it will precess, and it will create this sinusoidal variation of the transit times. And if you assume this is the cause of the variation, we get a precession rate that is, you can see here, that would imply a love number that is compatible with the one that we observe with the transit shape, from the transit, directly from the transit shape. In the future, we are going to continue to measure the transit, the deformation of WASP-103. We are actually obtaining data with KEOPS. We got at least 10 more transits, but we can reach more. We are observing at the moment, basically, WASP-103. And we hope that in the future we get a transit with JWST that will lead to a 12 sigma detection of the love number combined with our data, and that would allow a really good constraint on the core size of this planet. Also, we are interested in measuring the variations of the transit time, and for that we need to continue observing the planet's period, the transit, the times of transit, see how they evolve, if they start decreasing or they continue increasing, and we also are going to try to constrain better this other star that might be bound with WASP-103. And that's it. Thank you. I would like to thank the KEOPS team for the amazing work that allows us to get this very precise instrument that is reaching better precision than KEOPS for much brighter systems, than Kepler, sorry, but for much brighter system, and that allows to get this nice measurement of the deformation of a planet. And I'm happy to answer any questions.
Thank you, Susana, very much for this very interesting talk. We now have some time for questions. If you joined us on YouTube, please put your questions in the comment section. If you join us here on Zoom, please raise your hand and ask your questions. Questions? Okay, while we wait, my camera is not working again. Well, Susana, what is the planetary radius limit to try to detect this type of effect? Only hot Jupiters, or could we try to do something like with Saturn size or Neptune size planets?
I think we could be, but there's not known Saturns in structured orbits. The ones that we know are around the Jupiter, and then we have very small ones like Earth size, a bit larger, maybe 2 Earth radius, but otherwise very close to the star. There's not a very large variety, but really close. I'm saying in between, with orbits of 1 day. We have planets either very small or these much larger. Probably because the other ones have fall already into the star.
Okay. Oh, thank you. Julio, you have a question? Go ahead.
Yes. Hi. You mentioned in your last slide that the Gaia may help also to constrain the a possible companion through with the parallax. But do you think that well, in some cases Gaia may also be sensitive to the presence of the companion, and this presence may be reflected in the determination of the proper motions? Do you think that it will also be something that may help you? That is the possibility that the proper motion is not the one expected for a free body.
Yes, indeed. So we tried to use the data from Gaia already, but in the last release, I'm not completely sure if they already got much more information with the new release. We were going to look into it. We didn't have enough information, but when we have all the complete parallaxes or or their models, we will be able to hopefully we'll be able to measure if there is a star that is bound to WASP-103. For now, the parallaxes have a huge error. So there was a difference in the parallax of the first release of Gaia, and that led to a difference in distance of half. From the first parallaxes, the difference of the distance to the system went by half, and this is because we think that the measurements of Gaia are being it's being interfered, or it's being there's another star there that is changing the parallax of WASP-103, and then you cannot really trust completely the results. But I think that we will have to wait for the later releases to get the full orbits for this companion.
Okay, thanks a lot.
Thank you, Julio. More questions? I have another question, Susana. It's concerned to the shape of the light curve. Basically, what we observe is actually the projected, the effect will be embedded in the projected shape that we are seeing. That's it.
Yes.
The radius doesn't get shorter, does it? When it's passing in the center of the star, at the center, in the mid-transit.
The planet, the radius is smaller because the planet is showing you the smallest axis at mid-transit.
Yes, yeah, that's what was my doubt. I was trying to.
And actually, you can also see a slight decrease of the poles due to rotation.
Okay. Yes.
Besides this long axis, the poles are shorter than the equator, and we can see that. Like you can see that here. The rotation part you see in this first ingress and egress, and then the bulge is the part of the long axis of the bulge. Sorry, the middle bit is due to the bulge.
Okay. Another question will be, would be it? Does this tidal, does this effect can cause tidal heating in the planet and maybe observe?
Yes, sure. So one of the
infrared.
In the infrared.
Yeah, yes, during the outside of the transit, like modulated light curves in the infrared due to heating.
This I don't know. The observations of difference in the infrared to this from internal heating, I don't know. But I know that one of the explanations for these planets to be inflated is actually tidal heating. But it's expected to create some tidal heating. The question is how much and what is the signature. This I don't know, but it's a nice thing to check. What will be the signature of the tidal heating in the infrared temperature?
And well, my last question. And besides James Webb, I don't know, will Plateau be able to observe this type of effect, because it's sort of aimed to look to very long periods in Earth-like planets?
Plato can do this. The problem is that these are very rare planets. As you see from this plot, that there are not many that can be seen. And Plato is going to observe just part of the sky. And for now, the part that is going to observe doesn't contain WASP-103. So, but it's not decided yet. right? They are trying to get the long stair of Plato, one in the north and one in the south. And for now, these don't contain our best targets. Maybe it was 121. I don't know. So it will be, you will have to be lucky. But then there's the short stairs that are not decided. So maybe from this we'll be able to get more observations. But the problem is that we cannot point Plato to where we want.
Yeah.
It's will be a lucky. We hope to be lucky with at least one of the planets.
Yeah. Well, maybe it will be some new planet will be found with such characteristics.
Yes.
Well, thank you. Another question? Okay. If there are no more questions, I think we will now wrap this up. Just a final message. This presentation will be available in our website and in Elenia's YouTube channel. Thank you everyone for attending, and a special thanks to Dr. Susana Barros. Thank you very much for taking your time.
Thank you for the invitation. It was a pleasure. Thank you.
Everyone, have a great day. Stay safe, and I hope to see you all again in our next webinar that will be in 2 weeks from now. Thank you very much.